Okay, so hello everyone. I hope you successfully completed the yesterday's notebooks because I couldn't see many questions, and I hope you understand the basics of probabilities because we're and linear algebra because today we're going to rely more on those topics covered yesterday. So, continuing with math, I want to introduce the concepts of eigenvectors and eigenvalues because I believe they're also going to be taught at the Q Silver course, but I really believe that this is quite kind of a necessary step in order to understand quantum logic gates and how they operate and what they give us. Then I will talk about introduce the notion of qubit and the superposition that qubit actually can be in the superposition of both 1 and 0 states, sort of like we talked about yesterday in case of the coin flip, which could be the result could be either heads or tails. And at the end, I will talk about measurement, what it means in quantum computing to do a measurement. So to begin with, I'll start with a simple problem. Let's say we have a matrix, which we'll call M, and we have a vector V. And we want to find such a value, lambda, that after applying the matrix to our vector V, the result will still be vector V times some lambda. You can think of it to give you an example, you can think of the unit matrix, identity matrix, I'm sorry. And if you have vector AB, then the result is also AB with the eigenvalue of 1. So the lambda is what we call an eigenvalue. It's eigenvalue, I believe it's comes from German and from the word eigen. And eigenvector is the vector that we found to be the same after we multiply a matrix. So how to find a eigenvector and eigenvalue? Well, let's try to bring both equations to one side. So minus lambda v equals to 0. Then we can factor out the vector. So m minus lambda equals v equals 0. And then what we actually want to do, because we cannot subtract a value from a matrix, so actually we will put a identity matrix in front of the lambda. V to find 0. And actually, in order to find the eigenvalues of this matrix M, we can also get the determinant of a matrix. Now we'll later talk to you about how this is found, those determinants. So actually, we can say that this must be equal to 0 in order to find eigenvectors and eigenvalues. This is very basics behind this concept, and I'll try to give you more of an intuition rather than a strict mathematical proof. But later, when we talk about quantum logic gates, I will give you examples, and we will calculate both the eigenvectors and eigenvalues of those matrices, because I believe it's quite important to understand the linear algebra to move on with the next steps. So now let's move on to qubit. And qubit, unlike in the classical representation of bit, the qubit can be in a superposition of both values. So we represent a unknown state of the qubit as psi. And as I told you yesterday, the physicists like to put different letters and things inside those cats. So now we have a psi, and it can be some vector 0 plus some value of 1. And this is in the orthonormal basis, as I explained to you yesterday. So it means that the scalar product of 0 and 1 is equal to 0, and scalar product of the 0 vector itself is 1, and the scalar product of vector 1 with itself, the length of those vectors are 1. So we yesterday talked about that the our coin had certain probability being heads and some probability being tails, and those numbers were given by the scalars in front. But actually in quantum computing, we define the probability of measuring state 0 as operator 0 on the state psi. And to the power of modulus and to the power of 2. So to calculate this, let's break down our vector psi to component A and component B, component of 0 and component of 1 cats. Now we can rewrite this as 0 as a 0 scalar product with 0, because the scalars are interchangeable, and also following the rules of multiplication of summation, we get something like this. And from those rules here, from the orthonormality, we know that this should be equal to 1, and this should be equal to 0. So therefore, our result is a square. By analogy, we can also show that the probability of measuring state 1 is also using the bracket notation. You can try to prove it on your own. It's very simple analogy. We can prove it that this is b squared. Because in that case, here, this term will become 0 and this term will become 1, and we will get b squared. So, but we also know that the states are orthonormal, and we want the normalization of the states to occur. So actually, the length of the vector psi should also be 1. Therefore, if we also follow this logic here, A0, I'll try to rewrite all the terms here, because I believe that doing it once you will remember always how those brass and cats work, and then it will be much easier for us to work on more complicated algorithms such as quantum teleportation and entanglement. So now when we multiply all the terms, we get a squared 0, 0 plus BAB 1, 0 plus AB 0, 1 plus B squared 1, 1. We know from the orthonormality of those vectors that this reduces to 1, this reduces to 0, this also reduces to 0, and the last term reduces to 1. Therefore, I forgot the square here. Therefore, the A and B, therefore the result is A squared plus B squared. But we also know from this condition here that this must be equal to 1. So in order to obtain a proper qubit state, those two parameters, a squared plus b squared, must equal to 1. And we can also visualize this on a 2D plane. And this is a very crucial step that in this case, we are talking about the real valued qubit. So the A and B in our consideration can only have real values. In general, qubits can be complex valued. So it can also have imaginary part. I will try to introduce you the imaginary part of those qubits using a block sphere. But you need to remember that these are two different representations, and I will talk about block sphere in a minute because I think it's very, very useful to understand the next concepts. So here we have our x-axis and our y-axis. And we can, as I showed you yesterday, we can represent both vectors in the xy plane. But now, in order the state to be a proper qubit state, you can choose any vector you like, but its length has to be 1. So actually, here's what represents the vector A, and here is what represents the vector B. So by the Pythagorean theorem, we now know that if we want our vector to be the length 1, the condition a squared plus b squared equals 1 must be satisfied. But you can also try to imagine the qubit. Instead of describing our vector as a and b, we can also describe it with an angle theta. Because we know that the length must be 1, we can also try to represent the angle theta. And now the value A should become cosine of theta. And the value B should become sine of theta. Okay. Do you have any questions by now so far? I don't see any, so I'll move on. So next we have the superposition. So you can imagine superposition as a flipping coin we talked about yesterday. So while the coin is flipping, you can say that you're not able to determine whether it's a head or tails because it's spinning and it's not in a stationary state. And it's very analogous to qubits. You can say that the qubit may be in a superposition of being 0 and 1 at the same time. If you, for example, take the A to be 1 over square root of 2 and B to be also 1 over square root of 2, and then you get A and B equal to 1 over 2. So so we have the 50-50% probability of measuring both states. So now let's go to quantum logic gates. Quantum logic gates. And they're quite different from the classical gates and the Boolean algebra because the classical gates, for example, an AND gate, as an input, it received 2 bits, 0 and 0, 0, 1, 0, 0, 1, and 1, 1. and the output of this gate and gate depends on both states. So if both states are the same, the result is 1. But if they're sorry, here will be 0, but also 0, 0. But if both are true, then results is should be 1. But in quantum logic gates, these are classical. The quantum logic gates rely mainly on matrices. And I will now talk about the X gate, the Hadamard gate, and the Z gate, because these are the gates that will be very useful in our considerations. So the X gate is defined as the NOT gate in case of our our coin flipping problem we talked about yesterday. So we can examine now the eigenvectors and eigenvalues of this X gate. In order to do so, we talked about the determinant, that the determinant of this matrix minus lambda identity matrix must be equal to 0. So now I will try to give you how this algorithm works. I see there's a question on the chat. Where are the quantum status as long as coin flips? Where in quantum states, as long as I don't really understand the question. If you could say it, I would be very, very grateful. Are we talking about values always in the range 0, 1 only? So its qubit is always a half. No, actually, no. We can talk about qubits. What do you mean 1/4 of a circle? I don't really understand. I mean, a qubit can be represented as a vector in the state anywhere along this plane, xy plane, as long as its length is 1. So actually, the qubit can also have a value of negative square root 1/2 and negative 1/square root of 2. And this is called the phase. And I will talk about phase a little bit later when we talk about the Z gates. But in general, those A and B's can be any real and complex valued also. Upper right part of the plane. So it is a full circle. Yes, it is a full circle, right? Exactly. The qubit can have value, all values that lie on this circle. Exactly. So now back to our eigenvalue problem. We need to calculate the determinant of such a matrix, which is 0, 1, 1, 0, minus lambda 1, 0, 0, 1, which is equal to, I'll try to write you step-by-step solution of this problem, minus lambda on the diagonal. And sorry for the inconvenience. Next, we will subtract the values in the left matrix from the values in the right matrix. Sorry, here I made a mistake. It should be just a calculator. So we have minus lambda, 1, 1, minus lambda. In order to calculate the determinant of a matrix, such as A, B, C, D, we need to find AD minus CD. This only works for the two-dimensional matrix. This is very important to stress that. But you can think of the determinant of a matrix as the area of the vectors after transformation. So if we have a matrix that after a transformation, one vector lands in A, C, and the second vector lands in the BD, then the covered area is something like this, right? And this area should exactly match the value AD minus CD. Okay, so now back to our problem. This must be equal to 0. So minus lambda times minus lambda minus 1 times 1 must be equal to 0. And there are two values that satisfy this. So let's calculate. This is lambda squared minus 1 equals to 0. So we can factorize this as lambda minus 1 and lambda plus 1 is equal to 0. And now we have lambda that may equal to 1 and lambda that may equal to minus 1. These are very important steps. And now we want to find the eigenvectors. So vectors that after this X transformation will stay the same. In order to do that, we need to place this lambda to this formula here. So minus 1, 1, 1, minus 1. And we need to find some A and B that satisfy the condition that this is also equal to A and B. So now by multiplying, we have two equations. A minus A plus B equals A. And also A minus B equals B. Now we can try to rewrite those equations in some other form. So now we have 2A, I'm sorry, my B equals to A. Or we can say that, so, no, actually it's not correct. I should think of something else. Because the A should be equal to B. Yes, I need a second. Minus A plus B equals A. Equals the eigenvalue, of course. So it's 1 times A. And here A minus B equals B. Therefore, from the second equation, we get that A minus A minus 2B equals 0. So A equals 2B. And now I got stuck out. So, but I know that the answer should be 1 over square root of 2 and 1 over square root of 2. And also the other eigenvector should be 1 minus 1 over, I'm sorry, 1 over square root of 2 minus 1 over square root of 2. I'll need to think about for a second for this particular example because I'm a little bit stuck in this case. But okay, let's go on and let's review how this gate, this X gate, how this X gate relies on how it operates on different bits. So how it reacts to our 1 and 0. So actually this is vector 0. and it's get transformed to 0, 1, as we talked about yesterday. We can also rewrite this in kind of different notation. So we can say that 0 by the x operator gets transformed to 1, and also 0, 1, 1, 0. This is vector what? Sorry, this is vector 1. Will be transformed to 1, 0. To 0. This is how the X gate works. Another gate that is very important is the Hadamard gate. And the Hadamard gate is defined as 1 over square root of 2 on the almost every entry. But the last entry here is minus square root of 2. And this is called Hadamard's gate. So let's review how this Hadamard gate acts on our state 1 qubit. It's a little bit tedious to write all the entries, but hopefully we can manage. And now to multiply, if you remember from yesterday's lecture, we multiply those two entries to get the first entry here. So this will be 1 over square root of 2. And also here will be 1 over square root of 2. But we can also rewrite this as 1 over square root of 2, 1, 0, plus 1 over square root of 2, 0, 1, which is then equal to 1 over square root of 2 of the 0 vector plus 1 over square root of 2 of the 1 vector. So it's very interesting now. So you can see that the Hadamard gate transforms the vector 0 to vectors 1 over square root of 2, 0, and 1 over square root of 2, 1. So actually, when we calculate the probability, this squared, I mean, the probability of, after the applying the Hadamard gate, the probability of measuring 0 state is 1 over 2, because it's 1 over square root of 2 squared. And the probability of measuring one state is also 1 over 2, because 1 over square root of 2 squared is equal to 1 over 2. And this is very special gate because it allows for the phenomenon of superposition to occur and to take different measurements. So now let's try to review how this Hadamard gate operates on bit 1. So let me once again rewrite the Hadamard gate. Which is now minus 1 over square root of 2. And this now operates on this vector. And the result is, in the first column, we get 1 over 2 times 0, which is 0, plus 1 over square root of 2. And in the lower corner, lower entry, we should get, this will be 0, and this will be minus 1 over square root of 2. So now you see that you have the minus here pops out. And we can factor this by using also the same strategy as above. Now will be minus 1 over square root of 2, 0, 1, which also can be rewritten as square root of 2, 0, minus 1 over square root of 2, 1. Okay, so to review, the state 1 is transformed through the Hadamard gate by 0 as 1 over square root of 2, 0 plus minus 1 over square root of 2, 1. So now the probability of measuring a state 0 is 1 over 2, because it's 1 over square root of 2 squared. And the probability of measuring state 1 is minus 1 over square root of 2 squared, which is equal to 1 over 2. So you can see that actually this phase, this minus here, is only relevant to the computation of quantum gates. This would be very important, for example, in the teleportation protocol. The phase, this minus, will matter. But when we calculate the probabilities, we lose the information about the phase. So we are not able to measure the phase of the qubit. We cannot tell whether it's in state -1 or ±. We can only get the statistics of the qubit behavior. Okay, so we have also one gate left, which is the Z gate, and it is defined as 0, 0, -1. And let's see how this gate reacts to a 0 qubit. And it actually does nothing because, I'm sorry, this is a 1, not 0. I made a mistake. So 1, 0, this is our 0 qubit. So the result is also a 0 qubit. But when we apply this gate, so this is 0. When we apply this gate to a 1 state, we get -1. So 0, -1, which is -1. So in other words, the Z gate applied to 0 qubit does nothing. We can also say 1. And the Z gate applied to 1 is transformed to -1. And as you can see, this is a simple eigenvector and eigenvalue problem. So the eigenvector of the Z gates is 0 and 1, and the eigenvalues are 1 and -1. Okay, are there any questions by far to this free gates? I can see there's some discussion on the chat. Why the value of matrix is negative? Why the value of a matrix as 2, 8, 2, 2, 2 is negative? You mean Hadamard gate here? Well, this is also, I mean, how physicists came up with those gates. I mean, they have to have a physical representation. And actually, the theory behind why there's a minus here comes back to theory of quantum computing. And it's maybe more intuitive to talk about spins. So the electron, I think that the best interpret while we have minus in here is to talk about the spins of an electron. So a electron can have a spin of 1/2 and -1/2, which is either aligned with magnetic field or anti-aligned with magnetic field. And those operators are also called these Z are also called a Pauli matrix. And the Pauli matrices operate on the spins of physical particles, and they define also how those particles should behave. And that's why we put minus here. Okay. I'm reading now the chat. If you have any questions, you can also raise your hand. Oh yeah, here's a quick introduction to the twice applying Hadamard gate. We can also see how that goes. So in a moment we'll calculate this. Okay, so now the Hadamard gate is quite strange. So you can see we can calculate how this operator behaves when it's applied twice. There's a comment here, all the rules apply to every qubit. Actually, you can explain. I don't really understand the question. All these rules apply to every qubit architecture. Can you how those rules apply to every qubit architecture? Well, in most quantum computers, the application of gates is used by shining a laser. So imagine we can have an ion trapped in an electric field, or in this case of the trapped ions, or we can have mm, a superconducting quantum computer, which the qubits are a LC, sort of a LC circuit. And in each framework, the operation of qubits is done by lasers. And those lasers can have different wavelengths, so different color. They can have different duration. So depending on how long you shine the laser, you can apply different gates and different rotations. So it's really non-trivial to show that all the universal quantum gates are capable of being applied to every system. Yeah, like trapped ion or superconducting. Exactly as I said, in case of the trapped ions and superconducting, the quantum gates are applied by shining a electromagnetic pulse, and then depending on the duration, the frequency, we can have different quantum logic, different quantum logic gates. So let's now see what state could we obtain by applying Hadamard gate twice to, for example, a 0 qubit. And now we'll take a slightly different strategy. So now, instead of writing all the matrix, I will use the bracket notation. So after applying the first Hadamard gate, we get, as we remember from previous calculations, we get 0 plus 1/2, 1. Now, let's apply the Hadamard gate to both qubits, to both states. Now we have 1/2 times 1/2, 0, plus 1/2, 1. And this is our state 0 from before. So this state 0 gets transformed to this value right here. And our second qubit gets transformed to the expression 1 over square root of 2, also 0. But now we need to introduce the minus sign. Now, when you add both of them together, here you see that we have a minus sign. And here we have minus, and there we had plus. So those terms will cancel each other out after the summation. So what we're left with is state 0. And actually, you can actually also show that applying Hadamard gate twice to a one qubit, one state, it will also result in 1. And this is true also for every for the Z gate and for the X gate, for the NOT gate. Now I want you to I would like to introduce a concept of block sphere, because I believe it's very useful representation of how those quantum gates work. But it unfortunately involves also imaginary numbers, which we won't unfortunately cover here. But you can think of the X gate as rotation along the x-axis. So now, instead of writing the 1 and 0 in the xy plane, we now sort of expand our plane to 3D, and the vector 0 is our plus z axis, and vector 1 is on our minus z axis. And the x gate, you can think of the x gate as rotation about the x-axis. So you can see here that the 0 transforms to 1 and 1 transforms to 0. This is exactly what happens. So after the rotation about 180 degrees of the block sphere of the 0, you will end up in 1. And after rotation from state 1, you will end up in state 0. So this is our X gate. The Z gate, on the other hand, is rotation about the Z axis, because the state 0 rotated about the Z axis is also state 0, right? But state 1 rotated about, this is quite strange, and I don't really know how to explain this using this block sphere analogy, but imagine a rotating about the Z axis gives you this additional minus sign in front of the 1 state. But now the Hadamard gate is quite a strange gate, because it's a rotation about a x equals z axis. So you can see that actually a 0 state gets transformed to a point on the block sphere where it meets the x-axis. And also the y, the -1 gets transformed to no, sorry, not here, but here on this, we call it minus state. So we can actually confirm that this is the state, the eigens, this is I'm sorry, the plus state should also be the eigenstate of the x vector. So the this state is actually 0 plus 1 over square root of 2. And this is the superposition of both states. So when we apply the x gate to this plus state, we will get 0 plus 1 over square root of 2. Also, the x should stand in front. I'm sorry. I tried to write it a little bit nicer. Now we flip both bits, so it's 1 plus 0 over square root of 2. But actually, this is the same state we began with. So this plus state is the eigenvector of the x operator. Yes. Do you have any questions regarding this? Are 0 and 1 supposed to be perpendicular and not on one axis? Yes, that's very strange about the block sphere, because in the real value diagram, they are supposed to be perpendicular and are 1, right? So this is 1, 0, and I'm sorry, this is, yes, 1, 0, and 0, 1. But on the block sphere, it's a little bit different, because now we introduce the imaginary numbers. And now because of the imaginary numbers, in order to represent this on the single diagram, we would need a 4-dimensional space, because there are 2 numbers for each entry. So we can have a plus ib. If you're familiar with imaginary numbers, you would more understand this concept. But if you're not, don't worry, we're not going to touch imaginary numbers in this course yet. But I'll try to give you a brief explanation why they're not perpendicular here. So now, in order to fully describe the state, you need 4 numbers and 4 dimensions. But it's actually, we live in 3, so it's very hard to imagine it's very hard for us to imagine 4 dimensions. Therefore, we skew a little bit our representation so that we are able to write at least 3 of them, three of those numbers in a block sphere and represent them in 3 dimensions. But therefore, we lose the graphical representation of being perpendicular. But the states are still 0, 1, and 1, 0. But it's a different graph from this one. I hope I answered your question, and I could see that there are some questions before. So we kind of squeeze 2 dimensions, real numbers, plane to fit it. Yes, exactly. That's how I would understand the block sphere representation. See the results of quantum operation. What about measurements in block sphere? Also used for visualizing the result. Yes, that's a very good question, and they really help for us to visualize the result. And I will now try to place another block sphere for clearer view. So when we have our qubit in state, for example, 0, I mean, imagine a measurement in our case. We would measure oh, sorry. Let's start once again. Recall the Stern-Gerlach experiment I talked about yesterday. So in this experiment, we had a silver atom, and depending on the spin of this atom, it could go either up or down. And in the case of spin being somewhere in between, it had 50-50% probability of being here and here. So what I like to think of is, imagine a qubit being a spin and an arrow somewhere. So now imagine this is an silver atom, and we know that its spin is parallel with the sorry, should be actually this is parallel spin. This spin is parallel with the external magnetic field, and therefore by measurement we will always be deflected here. So this will be our zero state. The qubit in this configuration will always be found downwards. But in case of the qubit entering our splitter, our experiment with the spin anti-aligned, we'll be deflected somewhere here. But now a atom with a spin not clearly aligned and not clearly anti-aligned, half of times we will get 0 and half of times we will get 1. So you can think of it as projecting this vector either to one of those axes with certain probability. And if you have a spin something like this, then the more times it will tend to be 0. So roughly 75% of chances we will find it in state 0, and 25% chance of finding in state 1. And this is how I understand and how I have the intuition, really, because the intuition is really important to think of the Bloch sphere and the measurement in terms of those states. But actually, the measurement is just the numbers. So you can measure the amplitude probabilities, a squared or b squared. And these are only the values that you are able to measure statistically in an experiment. Okay, are there any questions more? I hope I answered your questions, all of your questions. And yeah, I think, and also I have a very quick introduction to you from Qiskit. But in order to do so, I will need to change my computers because I have saved them on different files. So I will have stopped sharing my screen and reshare it from another device, hopefully. And now I'll give you a quick introduction to Qiskit and I'm sorry. Yes, I hope you can see my screen now. Yes, okay. So the Qiskit library, in order to execute the code, we first need to import registers. And we have a quantum register, a classical register, and a quantum circuit. In order to construct a quantum circuit, we first need to define a quantum register. But in this case, you say how many qubits you want in this quantum register, and we call this variable Q, and we call the register quantum. We also have a classical register. So after measurement of the qubit, we take a classical register, so our classical computer, to tell us whether the result of the measured qubit is 1 or 0. Then we construct from both the quantum register and classical register, we construct a quantum circuit. And we can apply a gate to this quantum circuit. So right now I have a X gate, and then I apply measurement. I say that I want to measure qubit 0, and then project the measurement to bit 0 of the classical register. Then, very simply, I can draw our circuit. And usually in quantum computing, the circuits are drawn from left to right. And along each line, we have the gates that are being applied to each qubit. Then we define a simulator to run our simulation of qubits. and then we can plot our results. So if I try to execute this code, hopefully it will manage. It's not defined. Here is our simulator. Okay. So now I have my circuit. I apply X gate, and now I can see. Actually, you cannot see in this example. Maybe I try to extend this view. Expand image. No, not this one. Sorry. This one. I want to expand this image. Yes, now you can see that all the measurements are in state 1. That all the qubits we measured after applying this X gate are in state 1. But now we can try to implement a different gate, a Hadamard gate. The Hadamard gate is just H. And we can see what happened now. So after applying a Hadamard gate, half of our qubits were measured to be in state 0, and roughly half of them were measured to be in state 1. Now you can play with those quantum gates and apply many more gates. For example, let's try now to implement 2 Hadamard gates with the same qubit. See, we have 2 Hadamard gates. And now let's see what happens. So now you can see that all the qubits were measured in state 0. And this is exactly what we calculated mathematically a few seconds earlier. Do you have any question to this codes here? Is block sphere a Hilbert space? Technically, I think yes, but I'm not a mathematician, to be honest. But I think yes, the block sphere can be represented in the Hilbert space. It's more of an advanced mathematics. Yes, a vector representing a qubit is described by a 2-dimensional Hilbert space. A block sphere is an imperfect representative of this qubit. Yes, thank you, Przemysław. Thank you, Przemek, for the explanation. Exactly. Yeah. Do you have any questions regarding the codes here? If not, then I think I can thank you for today's lecture. I hope you learned something new and understand a little bit what I was talking about. I'll try to send you the notes here so you can review them. And good luck with the notebooks.